Hello, today is June 3rd, 2024. We're going to talk about electromagnetism, and then today we are going to talking about Gauss law. So again, if we have a charge, positive charge Q, and then we try to find the electrical flux that penetrates through the whole surface of the sphere. So phi is equal to E dot A, and then if this is the radius R, then the E due to the point charge Q in the center of the sphere is going to be equal to K Q over R squared. That's what we learned in the previous lecture. And then A we can consider as the surface integration. Again, the integration with the circle, that means let me see, if this is a sphere, that's the integration around the whole circle. And then that dA. Okay. So notice the angle between the surface right here, which is that, and the angle of the electrical field, they are the same. So the cosine theta actually is cosine 0 degree. That actually turns out to be 1. So what we have is K Q R squared times the surface area, which is 4 pi R squared. Again, if we have a sphere with the radius R, the surface area is that. Again, recall earlier we said K is actually equal to 1 over 4 pi epsilon 0. So we plug in right here to replace the K. We got a 1 over 4 pi epsilon times Q over R squared times 4 pi R squared. So notice 4 pi cancel out, R squared cancel out, so the result is Q epsilon 0. Notice the R is being cancelled out, right? That means if we have another circle, the sphere, around the same point charge, the electrical flux for the outside the sphere is also going to be equal to Q epsilon 0, based on the exact same calculation, right? Since it is independent to the radius of the sphere. In other words, doesn't matter how large the ball is, the electrical flux is always the same. It's equal to the amount of charges being enclosed, and then divided by the electrical constant. So what if we have a charge, and then we have a random shape, right? So that we can always consider this as the one inner. This is the sphere, right? With radius R1. And then for anything right here, like for instance, this little square right here, we can draw a line perpendicular to that, right? So let me put this into a logic. So this, the red one is the surface area, the little area dA of this random shape. Here, that is the area of a sphere. That means if I draw a sphere with the radius R2, which is from here to here, I can draw it, right? Any points, I can draw different spheres, right? See, if the angle right here is theta, then the direction of the little surface, because the little surface is perpendicular to whatever the plane it is, right? So that is also theta. So if this is the direction of the electric field E, and then E times cosine theta would be the component of E such that it is perpendicular to the random shaped surface, right? So if we found E dot A, then we can view this as the perpendicular components with little area of the A, and then we combine them together based on, what we derived right here. Then even though for the random shaped enclosed area, then the electric flux is still going to be E dot dA. And then that is equal to the electric charge divided by electrical constants. And this is the ENCLOS, enclosed. In other words, if we have a sphere like that, if we have a charge outside of that, then the electric field is going to be passing like that, right? So on and so forth, so on and so forth. Then if we look at the electrical flux, which is about this area, it's going to be E dot dA. Again, it is the complete integration of the surface. Then notice this enclosure does not include any charge at all. So that is Q enclosed epsilon 0. That actually 0 over epsilon 0, because it doesn't include any charge at all. So that's why the electrical flux is 0. So that recall a few days ago, when we calculate the electric flux for Q, right? Whether the electrical field is perpendicular to those two faces, or it is just a random one, like remember the model we had it before, or it doesn't matter whether the electrical field perpendicular to those two planes, or it is just a randomly direction. The electrical flux is always 0. Did you recall that? So that actually is the Gaussian law. The Gaussian law basically says the total flux that passing through any random closed shape that actually is equal to the completed surface integration of E dot dA, that equal to the Q enclosed over epsilon 0. So that's the Gaussian law. Okay, so this is a very important. There's a couple more law that is similar to this with equal importance. We're going to talk about later on, but this is the first law I want you guys to memorize. This is super important. And with this in mind, it will quickly help you to calculate doing some related calculations. So keep that in mind. So again, it's the one surface enclosed the charge, and then the total flux will be the charge included divided by epsilon 0. That is the Gaussian law. Thank you. Talk to you later. Bye-bye.